Bueno, gracias por la invitación para hablar. Yo lo que vamos a tratar de contarles hoy es una construcción que me salió bastante de casualidad hace poco, de un sistema estratificante de rango finito, o sea, de tamaño infinito. La cual, digamos, viene a contradecir una idea que tenía Eduardo, de que uno podía encontrar una cota para el tamaño de los sistemas estratificantes en la categoría de módulos de un álgebra. En la charla, digamos, van a haber esencialmente cuatro partes. Al principio les voy a dar un poco de historia y overview de dónde viene el problema, y voy a tratar de mostrar las conexiones con los orígenes en álgebras de Lie y categoría de peso máximo. Después voy a hablar un poco de módulos inclinantes y algo de categorías de peso máximo desde el lado de teoría de representaciones de álgebras de dimensión finita. Y después, al final de la charla, voy a tratar de dar un poco más lo que son los resultados, digamos, que he obtenido en este sentido. La primera sección va a ser sobre lo que es el álgebra homológica de orden superior que introdujo Iyama, y cómo eso nos ayuda a construir ejemplos de sistemas estratificantes. Uno de tamaño infinito, que es el que prometí en el título, y después también otros más que crecen muy rápido y que fueron en realidad mi resultado inicial. Y después voy a hablar de un resultado, o sea, si me da el tiempo, ¿no? De un resultado que obtuvimos con Octavio Mendoza en un paper que salió publicado hace unos meses en Documenta, en cómo uno puede construir sistemas estratificantes usando la teoría de tau-inclinación de Adachi, Iyama y Reiter. Entonces, bueno, este es, digamos, más o menos el mapa conceptual de dónde están, o sea, de dónde surgió las ideas, es en categorías de peso máximo, con el estudio de Klein Partial Scott, Klein Impartial en diferentes artículos, y la idea es ir desde empezar acá y terminar acá, ¿no? En la otra esquina. Entonces, bueno, como les decía, la noción de categoría de peso máximo, un poco Pablo ya nos contó hace 2 semanas, cómo estaban inspiradas en el estudio de la categoría O asociada a álgebras de Lie. Y lo que probaron Klein, Partial y Scott, y después también Tlab y Ringel lo siguieron estudiando, es que si vos tenés una categoría de peso máximo de rango finito, o sea, con un número finito de simples, esa categoría es equivalente a la categoría de módulos de un álgebra cuasi hereditaria. La noción de categoría de álgebra cuasi hereditaria tiene una definición bastante complicada, con recolmons y otras cosas que voy a pasar bajo la alfombra, porque hay caracterizaciones mucho más lindas y mucho más fáciles de hacer. Ahora bien, el tema es que tanto las categorías de peso máximo como las álgebras cuasi hereditarias están basadas, o sea, muchas de las propiedades que uno quiere estudiar se basan en los que se llaman los objetos estándar en estas categorías. Entonces, lo que hizo DLAB fue agarrar los objetos estándar asociados a las categorías cuasi hereditarias y pasarlos y definir algo un poco más general, que son las categorías, las álgebras estándarmente estratificadas, que esencialmente lo único que hace es olvidarse de una de las propiedades de los objetos estándar en las categorías cuasi hereditarias. Lo que me llamó muchísimo la atención mientras preparaba la charla es que, de hecho, estas álgebras cuasi estándarmente estratificadas, definidas por DLAB, de hecho fueron estudiadas por Futorny, Koenig y Mazurchuk Sí, ellos los estudiaron las usaron para estudiar la categoría O de ciertas subálgebras parabólicas. No sé qué es lo que quiere decir eso, pero de hecho probaron que la descomposición en bloque de la categoría O de de una subálgebra parabólica de SLN, creo, le da, digamos, cada bloque es la categoría de módulos de una álgebra estándarmente estratificada. Lo cual para mí, de hecho, fue una sorpresa cuando estaba preparando la charla. Ahora bien, estos objetos estándar tienen muy lindas propiedades, pero son objetos estándar que están muy asociados a los módulos proyectivos de estas álgebras. Entonces, lo que hicieron Erdmann y Sáenz fue definir los objetos, o sea, definir una generalización de esto, que son los sistemas estratificantes, de los cuales los objetos estándar son un caso particular. Y esos fueron muy estudiados por Mendoza, Marcos, Eduardo, Octavio Mendoza y Corina Sáenz en una serie de papers que hasta el día de hoy siguen haciendo. Por el otro lado, vamos a ver un teorema de Henning-Krause que relaciona mucho los objetos estándar de las categorías de las álgebras cuasi hereditarias con las secuencias excepcionales. De hecho, las secuencias excepcionales vienen de la geometría algebraica, y digamos, y a la teoría y dentro de lo que es teoría de representaciones de álgebra de dimensión finita, fueron introducidas para álgebras hereditarias. Y entonces, para ese caso, para álgebras hereditarias, digamos, las álgebras hereditarias son en particular cuasi hereditarias. Entonces, los objetos estándar de las hereditarias constituyen una secuencia excepcional, tal como fue definida para la geometría algebraica, pero bueno, en general, objetos estándares vamos a ver algo respecto a eso. Y estas secuencias excepcionales después no se estudiaron mucho en la categoría o sea, en álgebras de representación finita, se estudian mucho más en geometría algebraica, pero en el 2015 Igusa y Todorov definieron las secuencias excepcionales con signo para estudiar un cierto fenómeno que venía de las álgebras de conglomerado, y esas fueron luego generalizadas para toda álgebra de dimensión finita por Bonn y Marsh, a lo que se llaman secuencias tau-excepcionales. Y es como el nombre, o sea, la letra griega tau lo indica, tiene algo que ver con la teoría de tau-inclinación, definida por H. y Reitman. Resulta que con Octavio Mendoza nosotros probamos que la teoría de tau-inclinación nos permite obtener sistemas estratificantes, y esta conexión que se veía acá, que vamos a ver que definió Krause, de hecho se recupera acá, porque nosotros con Octavio también probamos que los sistemas estratificantes que encontramos usando la teoría de tau-inclinación son un caso particular de secuencias tau excepcionales. Y bueno, y la otra cosa que quiero comentarles hoy es lo que es hacerles una pequeña, muy pequeña introducción a lo que es el álgebra homológica de orden superior, que introdujo Iyama. También, digo, estas tres, tanto la teoría de tau-inclinación como el álgebra homológica de orden superior, son cosas que aparecieron generalizando ciertos fenómenos que aparecían en las álgebras clúster y en las categorificaciones de las álgebras clúster, y resulta que estas dos cosas nos permiten construir sistemas estratificantes de forma bastante natural, y de forma bastante inmediata. Bueno, un poco el setting de mi charla, siempre que yo digo álgebra, quiero decir es un álgebra de dimensión finita sobre un cuerpo algebraicamente cerrado, ¿no? Y mod A es la categoría de módulos a derecha, que son infinitamente presentados. Y cuando yo diga int A, quiero decir la subcategoría plena de indescomponibles, ¿no? En mod A. ¿Qué es un sistema estratificante. O sea, en vez de empezar por las highest weight categories, o sea, las categorías de peso máximo, y llegar hasta sistemas estratificantes, voy a hacer en la charla el camino inverso. Y voy a empezar definiendo lo que es un sistema estratificante. Sistema estratificante no es otra cosa que es un conjunto ordenados con un orden lineal, tales que, como digo, están ordenados linealmente, y además tenemos dos condiciones respecto del OM y respecto del EXT. Esencialmente, los morfismos respetan el orden impuesto, y las extensiones también. ¿Sí? Y ningún objeto, y todo objeto es rígido, digamos. No hay o sea, hay extensiones solamente en el orden que está impuesto en este orden acá, y hay morfismos en ese mismo orden. Entonces, puedo ir para un solo lado, ¿no? Cuando tenemos una categoría, una álgebra hereditaria, es muy fácil de ver que uno puede construir un sistema estratificante usando los proyectivos, porque la álgebra hereditaria tiene un quiver que es acíclico, necesariamente. Entonces, ese quiver te da un orden en los proyectivos, ¿no? Y entonces vos sabés que tenés morfismos hacia donde van las flechas, entonces vos podés ir hasta el final de las flechas e empezar a ir para atrás para construir con los proyectivos un sistema estratificante. Bien, eso es un sistema estratificante, y además decimos que un sistema estratificante es una secuencia excepcional. Sí, el endomorfismo de cada uno de los objetos indescomponibles que tengo, el álgebra de endomorfismos es isomorfa acá, ¿sí? O sea, porque en general este álgebra de endomorfismos es un álgebra local, pero puede tener elementos nilpotentes, en este caso no los tiene. Y además lo que le pedimos es que no hay ningún tipo de extensiones de orden superior. O sea, todos los n, para cualquier n natural, o sea, se anulan para el mismo orden que teníamos, ¿no? O sea, en el mismo orden de los que impusimos acá. Bien, para seguir hablando y para hablar de las propiedades que tienen los sistemas estratificantes y demás, y cómo uno llega a las álgebras cuasi hereditarias y estándarmente estratificadas, uno tiene que hablar de lo que es la categoría filt X, donde X es una subcategoría de moda, y que es esencialmente todos los módulos que están filtrados por objetos en X, ¿no? O sea, esencialmente tenemos una cadena ascendente de subobjetos, tales que los cocientes sucesivos están en la subcategoría que yo definí al principio. Bien. Ahora bien, ¿qué es una álgebra estándarmente estratificada? Esencialmente es una álgebra estratificada o sea, es una álgebra tal que como módulo a derecha está estratificada por sus módulos estándar. ¿Qué quiere decir con esto? Quiere decir que existe un sistema estratificante, ¿sí? Tal es que todos los proyectivos están filtrados por este sistema estratificante. Este sistema estratificante es lo que se llaman los módulos estándar del álgebra estándarmente estratificada.
Perdón,
y además,
Hipolito, una pregunta tonta. ¿El sistema estratificante es sobre la categoría de módulos?
Sobre la categoría, sí, en la categoría de módulos, sí.
Okay.
Sí, adentro de moda. Sí, esto es adentro de moda. Déjame escribirlo acá, así ya queda. Sí. Entonces.
Perdón, Hipolito, creo que se conectó Hagen.
Hi. I will switch to English now. So the idea is that standardly stratified algebra is an algebra which is all the projectives as a right module are stratified, are filtered by the standard modules, right? So we have so now the existence of one stratifying system is not, it doesn't imply uniqueness actually. I mean, you can build several different stratifying systems such that a field is standardly stratified. So in general, the standardly stratification of an algebra depends on the stratifying system that you choose, right? So there are properties that one shows in that way. Moreover, a standardly stratified algebra is quasi-hereditary if, as before, the endomorphism algebra of each lambda module of each of the standard modules is isomorphic to the ground field. One interesting thing is that Henning Krause showed. So Henning Krause put a paper on the archive in 2015, and in that paper, he characterized highest weight categories in terms of recollement. All abelian highest weight categories in terms of recollement, and he showed that if you take the standard modules of a quasi-hereditary algebra, then they form an exceptional sequence, which is something quite strong, because actually he showed that a highest weight category, okay, is equivalent with finitely many simples, is equivalent to the module category of a quasi-hereditary algebra. And what he showed is that you can build a series of recollements such that these recollements allow you to carry the x's along. And then since the first guy is projective, all the x are 0, and this allows him to conclude that all the x n's for each n is 0 in the whole module category, which is quite strong, and I was quite surprised about it, and I got carried on and so on. Well, so what do I mean? So okay, now suppose that we have a stratifying system, right? Theta with a linear order. Marcos, Mendoza, and Sáenz, they showed that if you have a stratifying system, any stratifying system, you can always find n short exact sequences of this form, where you have theta I, which is your element in your stratifying system at the end, and you have two other objects, pi and qi, where qi is filtered by the thetas which follow, right? And moreover, that all the all the pi's are x projective in the category of filter modules. So the x1 of pi with x is always 0 for all x in these filter modules, right? And moreover, they showed that the endomorphism algebra of this sum is a standardly stratified algebra. Okay, with the same and these guys actually get carried into the standard objects of this standardly stratified algebra, which is quite a nice result, I find. And then these are the guys. So when in highest weight categories, according to what I understood, when in highest weight categories they study this tilting, when they call tilting modules, they call these tilting modules to these pi's, right? That there seems to be exactly one for each weight, right? And then you take the endomorphism algebra of these guys, and this gives you a module category of a quasi-hereditary or a standardly stratified algebra. Now, the definition this is the definition. This is of Miyashita. Actually, let me put it here. This is Miyashita. So this is the definition of a generalized tilting object. An object T in mod A is generalized tilting if these three conditions are verified. First, that there exists some natural number such that the projective dimension of T is less or equal to this n. Secondly, is rigid for all I in the natural numbers. In general, alternatively, we can say that this is rigid, right, for I less or equal than n. right? Because since the projective dimension is at most n, the other x will vanish per se. And we ask, the third condition is the existence of an exact sequence of this form. So essentially, you want that the algebra, so all the projective objects in your algebra is you have a co-resolution by elements in at t. Now, this is these tilting objects are quite powerful, allows us to get derived equivalence between finite dimensional algebras and so on. And there is one clear example, and in this case is all the projectives form naturally, yeah, a tilting object. And when you do the endomorphism algebra of these guys become actually the projective objects in the algebra. So yeah, I still trying to, yeah, so they're automatically tilting in the weight of highest weight categories. These guys are automatically tilting in some category. I don't know what happens in the bigger category O, but within the module category, of course, they are tilting because they are projectives. I mean, they are the algebra itself. So this is how you get it. Now, that being said, I will pass to higher homological algebra, right? So higher homological algebra was introduced by Yama. So, and he was studying actually he was really interested in the categorification of cluster algebras using cluster categories. And in this categorification, the clusters in cluster algebras were cluster tilting objects, two cluster tilting objects at the beginning of some triangulated category called the cluster category. Now, this the definition of a two cluster tilting subcategory or a D. So if you will fix any D, the D cluster tilting subcategory is the following. Essentially, a D cluster tilting subcategory is a category which is maximally self-orthogonal. Okay, it's a collection of objects could be in a triangulated category, but in this case, we chose to put it in the module category. It's a collection of objects such that there are no extensions for I equal from 1 up to D minus 1, where we fix an integer D. There are no extensions of order I between any of the objects, and it's maximal with respect to these properties. If you take any object in the module category, verifying these two conditions, having no extensions in one side or the other, it should be already in your D cluster tilting subcategory. Okay? And of course, with this definition, if we take any algebra, the module category mod A of A is a one cluster tilting subcategory because this condition becomes empty, right? So every module should be there, and the one cluster tilting subcategory of mod A is the whole mod A. Okay, and why we care about this? Well, we care about this because of the Hires-Lander correspondence. That was one of the main breakthroughs in this theory. And the starting point of the theory, which was showed by Yama, in which he showed a one-to-one correspondence between algebras having a D cluster tilting module. Okay, a D cluster tilting module is a module such that the additive category generated by M is a D cluster tilting subcategory. Okay, so it means that we have finitely many indecomposable objects in this D cluster tilting subcategory. And we take the sum of all of this. Okay, if we have a module in this, with these characteristics, if you have a D cluster tilting subcategory, and you take the endomorphism algebra of this module, you obtain an algebra gamma with the following, with these conditions, that such that there is, the global dimension is at most D plus 1, and the dominant dimension is at least D plus 1. And actually, this induces a bijection, and this was
sorry. What is the dominant dimension?
So the dominant dimension is that you start with A. So you start with A. If I'm not mistaken, you start with A, and then you take a projective injective modules. So you do the injective modules. No, I don't remember. Sorry, I don't remember. The idea is that you have some resolution by projective injectives, and then you take the minimum of those. So the minimal resolution that you could get of objects by projective injectives.
Okay. And do you have an easy example just to see?
I mean, in general, this coincide no, I didn't. Sorry, I didn't want.
Okay,
to,
no problem. Go ahead.
But the thing is, as a sort of, yeah,
sorry. So, how do you go in this correspondence from an algebra A to the algebra gamma? I think you mentioned this before. But...
This is the endomorphism algebra of your D-cluster tilting subobject.
Okay, so you could construct the. So in an example, what do you get? You start from an algebra A equal something well known, and then what do you obtain?
So, for instance, so the well-known case that this I know for sure is the case D equal to 1, which was the classical Auslander correspondence, which was back in the 70s, I think. Which, if you take D equal to 1, the one cluster tilting subcategory is the full module category. And what Auslander had shown is that there is a one-to-one correspondence between algebras of finite representation types, because having a one cluster tilting object, it means that you have a one, you have finitely many indecomposable objects in your module category. And then if you take one copy of each indecomposable and you do the sum of all of this, you take the endomorphism algebra of this guy, and it's an algebra having global dimension at most 2 and a dominant dimension at least 2. This is the classical set. And actually, then because you have this correspondence, for instance, this is what this object that I just told you is what is called the Auslander generator of your algebra. And then people started studying, okay, what happened if you have an algebra of infinite representation type, which is the minimum of the global dimension of this endomorphism algebras, because this guy is a generator, co-generator. And then, for instance, Sonia has studied a lot this kind of objects, which are the Auslander generators. And this is quite related to the rep dim of your algebra, to the representation dimension of your algebra. So this is a problem which is that problem stems from this bijection as well. I'm sorry, I don't remember exactly what is the dominant dimension of an algebra, but if someone has an idea in the public, don't hesitate to interrupt me in that respect.
I just checked.
Yeah.
And the definition is almost the one you said. So you have to have a resolution by projective injective objects.
Yeah. But
the point is that it doesn't have to go to the end. So you have A goes into M1, which is projective injective, then to M2, which is projective injective, and so on. But it doesn't have to end at a 0. Just end at some point.
Okay.
That has to be a complex, an exact complex, and all the M's have to be.
And is the infimum of these guys, or
and the infimum of the length
of these resolutions that you have? Yeah. Sorry, Hagen, you are muted, it seems. We cannot hear you, sorry.
You are still muted. No, not now.
No, I think now it. Okay. Okay. Yeah. So yeah. So this is so the classical result by Oslander was pretty big. People have cited that paper quite a lot and have studied consequences of this theorem a lot. And then Iyama went and said, you know, we can actually maybe no. Now you're muted. Maybe you could. I think you are unmuted, Hagen, now. Okay.
Maybe it's the computer's microphone.
Ah, okay. Yeah. So
you can use the chat if you want.
Of course, yeah. So the idea is that this started a lot of the quest of finding higher results for a lot of things, right? I mean, and nowadays we have n abelian categories, n-torsion classes. For instance, I have a paper with Sibile, Javada Sodalagic, and Peter Jorgensen, in which we study n-torsion classes. There are people studying, there exists a notion of n, one of the things that exists for every module category is the Oslander-Wrighton translation, right? So you actually can define a higher Oslander-Wrighton translation as follows. What you do is, given an object M and a module M, in order to get the D Oslander-Wrighton translation, you take the D-1 CCG of this guy. So you have the classical CCG, you take the D-1 CCG of this guy, and then you apply the classical Oslander-Wrighton translation. Okay, this might seem arbitrary, but it's not so arbitrary because actually you can show a number of things with these guys. For instance, you could show that there exists a higher Oslander-Wrighton formula using these guys, in which essentially the higher Oslander-Wrighton formula says that the hom, so that x n a m tau mn is isomorphic to the dual of the hom a n tau xd, tau d of m quotient, but all the projectives to all the maps that factor through the injective modules. This, when d is equal to 1, is exactly the classical Oslander-Wrighton formula that we will use later on in the talk. Now, one needs to say something which is really important, is that in general, if you give me an algebra and you say, hey, is this guy having a D-cluster tilting subcategory? Well, the answer most probably will be not. And the quest of finding examples of D-cluster tilting subcategories is also an area of active research, right? I mean, people have been studying that a lot. And all the cases that we know of D-cluster tilting subcategories are of finite type. So there are cluster tilting subcategories which are the add of some cluster tilting object. So there are no infinite D-cluster tilting subcategories just known in the literature just yet, right? So that was the problem that Iyama, Herschen, and Opperman were studying at some point, and they were trying to construct a cluster tilting subcategory, D-cluster tilting subcategory with infinitely many indecomposables. And for that, they defined, they showed a lot of results which allowed them to define the notion of a D-representation infinite algebra. One example of such algebra is the Bellinson algebra, which is quite popular in algebraic geometry, in which the D, so I still stick with my D. The D Bellingson algebra has D plus 1 vertices, all in one line, and between two consecutive vertices, we have D arrows. And then we have this ideal of the relations such that if you go with one arrow here and then you compose with one arrow there, it's the same. So we have the commutativity somehow, right? So going from this arrow and then this arrow should be the same as doing this. This is for every pair, quadruple of arrows somehow. This is a well-known algebra. And inside there, they defined several subcategories. And the first subcategory that they define is this higher post-projective and higher pre-injectives, which are exactly what you would imagine. You start with this BD is the algebra itself, right? Is the sum of all the indecomposable projectives. And then you take the inverse of the D is Auslander-Reitens translation for every I that you have there, right? So you do infinitely many inverses of Auslander-Reitens translation of the projectives. This is PD. And then, so this is the curly PD. So the straight PD is the indecomposables of this category. Dually, the curly ID is you take the this is the dual. Sorry, I made a mistake. This is so you take the injective objects of this algebra, and you take all the successive this Auslander-Reitens translation, right? You apply this Auslander-Reitens translation, and then again, and so on and so forth, right? And then doing that, then you take the straight ID is the indecomposables of this category. They go along and they show a number of results, and actually they also define another category, a third category, RD, right, which is somehow associated to the indecomposables, which with the post-projective and pre-injective, which is almost D-cluster tilting. What is almost D-cluster tilting? The fact is that there are some objects in the module category which have no extensions with any of these guys, but however, they are not self-orthogonal. So in particular, if you have anyone here, the x1 of every object with itself would be 0, right? By the definition of a D-cluster tilting subcategory. And to show a pictorial way, they show that this in this Bellingson algebra, you have a situation much like in the Kronecker quiver. You have some kind of higher Auslander-Reitens quiver as well, and you have something like this. You have something like this going on, where here you have the injectives, here you have the projectives, and then you have this component, which are the regular components. So you have the post-projectives, the pre-injectives, and the regular component, which is exactly the Auslander-Reitens quiver of the Kronecker algebra, right? I mean, this is our classical example, but in general, this works for every Bellingson algebra for D greater than 1, actually, because for D equal to 1, we have the case A2, and this is not true. But for D greater than 1, we have this situation. Among all the results that they show in order to make this nice drawing, they show that first, there are in PD and ID, there are infinitely many indecomposable objects. Not only that, they show, as I said, this is an almost D-cluster tilting subcategory, so there are no x1s between anyone here and anyone there, right? And even more, they show that as in the Kronecker case, there are morphisms going. So actually, as in the Kronecker case, in this general case, you have the same. You have morphisms going from left to right. So this is really a higher version of the Auslander-Ruyten-Quiver of the Kronecker somehow, right? So you have only morphisms going in this direction, right? So in particular, this implies that there are an order in the composable objects in PD and ID, such that there are no maps going from X to Y if Y is smaller than X, right? So since I have an order in which I don't have any maps, and moreover, for any pair of objects that I have in PD, I have no extensions between them, then necessarily with this order, PD is a stratifying system, which is infinite. Likewise, ID has the same properties, and actually one can construct this would be difficult to do, but we could be able to consider PD union ID with a certain order to have an stratifying system that starts somewhere, that finishes somewhere, but in the middle has infinitely many things, which actually comes as a big surprise. And actually, they put it in this paper, Herschen, Yama, and Opperman, that this came to solve a question that Yama had also for some time, in which he was wondering if such infinite collections of X orthogonal objects existed or not. I mean, for him, it was not necessarily clear, and he was able to actually go and construct one with his pulse. So this gives a nice example of an infinite stratifying system. But as I said, the Bellinson algebra is one example of the D-representation infinite algebras. They define also the notion of, for instance, of higher pre-projective algebras. And these higher pre-projective algebras also have a nice, they're D-representation infinite and so on and so forth. I mean, they show that many algebras are D-representation infinite. Now, another example, and actually this example of stratifying system was sort of given to me by Gustavo Jasso once he has seen this example that we show now, because actually the techniques are exactly the same. And for that, let me call Hn the path algebra of the quiver of type An, yeah, without any relations, the hereditary algebra. Then I would give a definition, although it's actually a theorem, which was proven by Yama, and I would call the D Auslander algebra An of Hn to be the endomorphism algebra of the D-cluster tilting module in the algebra D-1 Auslander algebra of Hn. So essentially, this is an inductive process. We know that Hn is of finite representation type. So it has finitely many indecomposables. You have a classical Auslander generator, and you take the endomorphism algebra of this guy. This is the classical Auslander algebra, right? Which I call one Auslander algebra of An. And Iyama showed that this guy has a two-cluster tilting subcategory. So you take the endomorphism algebra of this guy, and Iyama showed that this guy has a three-cluster tilting subcategory. And you take the endomorphism algebra of this guy, and so on and so forth. There is this inductive process that you could do defining all these higher Auslander algebras. And this goes as far as you want it to go. And moreover, he not only showed this existence of this recursive process of constructing higher and higher Auslander algebras, but he also showed that constructed explicitly the quiver and relations of each one of these higher Auslander algebras. In particular, he showed that the quiver is essentially the n simple is the d simplex in Rd, right? And you take the integer vectors in this d simplex. Okay, so what you have is this is inside Rd, sorry, right? So we are inside here Rd. So inside Rd, you have a simplex spanned by this vector. The origin here, and then the elements in the canonical basis of Rd, right? And you have finally many integer points inside there, which is essentially an hypervolume, right? This number is essentially an hypervolume. And not only that, these are the vertices of this quiver. He also builds the arrows of these quivers and shows that the quiver is acyclic. As a consequence of these two properties, we have that for each d and each n, there exists an order because the quiver is acyclic, we have an order such that there are no morphisms in one direction. And since we are this order is given in the composable objects of a D-cluster tilting subcategory, we know that there are no extensions in any direction. In particular, there are no extensions in the direction imposed by the morphisms. Hence, each one of these n-cluster tilting modules, D-cluster tilting modules in the Dn-1 Auslander algebra of Hn is actually a stratifying system in this algebra. But what is quite interesting, and which was the motivation that I got to, is that the number of in the composable objects of this guy is an hypervolume, but to the power of d, right? So this, when n goes to infinity, this grows of order I don't know if this is small o or big O, but this has is like x to the d, right? And because this is an hypervolume of but d-1 hypervolume, this grows like x to the d-1. So as n goes towards infinity, this quotient goes to infinity. So in particular, this shows that there is, if you take only finite stratifying systems, you also show that you cannot have a linear bound on the size of your stratifying system from the by the basis of the Grothendieck group of your algebra, which, I mean, I don't know if is extremely helpful, but it's quite interesting. I mean, it's a kind of nice result that I liked, and these are the examples coming from a higher Auslander-Ritten theory. Sorry, higher homological algebra. To finish, let me speak about the example that we built with Octavio Mendoza. With Octavio, we did, as I said to you, we built some example using the tau tilting theory, which was introduced by Adachi Yaman-Raiden in 2012, I think. And in order to tell you how you construct such a stratifying system, what I will do is essentially tell you how you construct in general a stratifying system using the projectives. For that, remember that the trace, so if you take a subcategory in mod A, as a category in mod A, and any object in A, the trace of X in M, we define it as to be the sum of all the images of all the maps going from any element in X to M, right? Because I am the module category, this is actually a well-defined sub-object. This is actually always a sub-object of M. I mean, we are in a finite length category, so this is contained and this gives us always a subobject. Now take the algebra as a module over itself, and then write this as a direct sum of indecomposable projectives for some order here. One can show that if you take theta I, so this set theta to be where theta I is the projective, the ith projective quotient by the trace given by the pj's which are with j bigger than I, what you obtain is a stratifying system, right? With the natural order given by 1 to n here. This is a stratifying system. And we can show it. I mean, and what we show with Octavio, and I will explain why in a second, but what we show in Octavio is that this construction actually can be generalized to every tau-rigid object. What is a tau-rigid object? A tau-rigid object is an object that has no maps to the Auslander-Ritten translation of itself, where this tau is the tau1. I mean, I told you about tau d. This is the classical tau1, right? One important consequence of this is that there are at most n indecomposable summands, where now n is fixed and is exactly the rank of the Grothendieck group of my algebra, right? So now the number, so the size of the stratifying system coming from tau tilting theory actually is always bounded by this guy. And how we show that? Actually, what we showed is that first, for every tau-rigid, there exists a decomposition of T as a direct sum of the TIs, such that TI is never a factor of the following TJs, right? So essentially, the first cannot be seen as a quotient of sums of all the rest. The second, it might be the quotient of the first, but no from the third on, and so on and so forth, right? So the theorem that we showed is essentially the same that I told you about the projectives, which was a classical construction. The theorem says that if you take this decomposition of a tau-rigid object and you do exactly the same construction, you take the trace of Ti by all the Tj's that j greater than I, then and you quotient Ti by this trace, then this gives you a series of indecomposables. And the fact that we needed the fact that this is not in fact of the sum in order to ensure that these guys were non-zero. So these are always non-zero, yeah. But once, not only they're non-zero, but because essentially one can show that these guys are in a torsion-free subcategory in the torsion-free part of a torsion pair, while all the theta's are in a torsion-free part. In the torsion part, there are no maps in this direction, and finally the x ones vanishing in the same direction comes from the Auslander-Ritten translation that I told you, the Auslander-Ritten formula that I told you before, that x1, this is a consequence of the fact that x1 theta I actually tj theta I is isomorphic to the dual of the Holmes quotient by the injectives of theta I tau of tj. And because by construction this stuff is so and actually we have an epi from d of Holm theta I tau of tj, and by construction we showed that this guy is 0, so in particular this is 0. right? And this shows that actually this guy is a stratifying system, and this is how you do it. Okay, I think I'm done for today. Thank you very much for your attention.
¿Preguntas?
Yo tengo un montón, pero creo que directamente te voy a pedir que en algún momento
Dale.
hablemos. Lo que sí te voy a pedir es la referencia del primer paper que mencionaste, era de Ringel, que levantaba estos resultados de X por Recolemont.
Krause.
Krause, ahí
Krause.
está, por eso no lo encontraba.
Krause. Es 2015.
¿Te acordás el título?
Highest weight categories and Recolemont, I think, actually, something like this.
Ok, perfecto. Gracias. No me quería.
Yeah, exactly that. Highest weight categories and Recolemont. This is the link. Now I put it on the chat. I'm still trying to understand this completely. I must say. I mean, this is. Yeah.
I need to see examples of things.
Okay.
More examples. I mean.
For instance, of.
No. For the things that you have been defining, because I'm not familiar, so I need to see examples.
Right. So, for instance, for A2, I can show you the construction for A2 of the So for A2, you start with, of course, A2. This is H. So you start with A2, right? And then the module category is 2, 1, 2, and 1. And then you take the endomorphism. So now this is
Can you share?
Yeah.
I don't know if you're writing, but if so.
Yeah, I need to share my screen. I'm sorry. Yeah, of course. Okay. So here we have A2, right? And then we have the object. So the Auslander generator is the whole thing. And if you take the endomorphism algebra, what you get is A3 radical square. Right? And then this module category, so the Auslander right quiver of this guy is something like this. Right? And actually, this, what Iyama showed, that this has a 2 cluster tilting subcategory, which happens to be this guy. This is the cluster tilting subcategory, right?
Okay.
And if you do the endomorphism algebra, actually you'll see that is like 1 goes to 2, goes to 3, goes to 4, right? And then you have okay, so, and you have radical square again. Oh, sorry. Right? You have radical square again. And but the interesting thing somehow is that this he realized that you could see this guy as this and that somehow. So this is a plane, and here you have another plane, right? So you have a sort of the triangle here and only one point in another plane, and this gives you the 2 simplets, right? And then you keep going, and then so what you would get is actually a 3 cluster tilting subcategory that should have how many? 3. Well, it would have 5 points.
Oh, yeah, okay.
And so on and so forth. And essentially the 2 cluster tilting subcategory of AN, so if you take, I don't know, A4, you start with A4, what you would get is you would get this guy first, and then you would have a copy of A3, and then you will have a copy of A2, and then you have a point, and then you would have maps, arrows in this direction. Somehow. Right? So it gives you really the 2 simplex here. Right? And then the Auslander-Ruyten translation, the higher Auslander-Ruyten translation, it goes in this direction. So this guy goes here, because now the almost split sequences, the 2 almost split sequences have 4 terms. So in this case, the 2 Auslander-Ruyten translation would have this. So if this, so in this module category, if you look at this module category, you have these 3 are projectives, right? So the Auslander-Ruyten translation is 0. And also the 2 Auslander-Ruyten translation is 0. But the 2 Auslander-Ruyten translation of this guy is actually 3. So it goes from here to here. Right? So you really get this idea of the simplex, and it grows, right? So yeah, that's how it goes. For instance, this construction of and something similar happens actually for sorry, yes.
No, it's okay, it's okay.
Okay.
Hipolito?
Yes.
I just want to say something that is sort of unrelated to this, but I have made the exact same drawing you just did some time ago, discussing with Futorni regarding on so the drawing at each level, the triangles and then the Auslander-Ruyten quivers that you drew are exactly the same as the diagrams we use with Futorni to describe some combinatorial objects that parameterize bases for finite dimensional representations of GLN. So the dot parameterizes representations of GL1, the peak parameterizes representations of GL2, then GL3, then GL4. And the downward going arrows you just drew are the ones I would draw to say that, so these patterns you build are built out of essentially this inclusion of GLN, I always pick in the top right corner. And if I want, then I wanted to go back and restrict from the lower right corner, or with respect to some parabolic subalgebras, I would draw the downward pointing, actually the blue ones.
Ah, okay, yeah, okay. These guys. Right.
So I have absolutely no. That's how you go up.
Right. These are the
with a certain, yes. And then the other one is going down through a different parabolic subalgebra. So I have no idea what the relation is, but I have drawn this exact same drawing in a completely different context.
That's pretty cool.
That's pretty cool.
Yes.
So now I have to read Futorni's work on parabolic algebras, and we have to
we should
down and do this.
Discuss about this, yes.
Sorry, got all excited.
Yeah, of course. No, it's good. Cool. Pretty cool. actually a relation that the thing is, I don't know how to describe these guys functorially, right? But the relation, so GLN would correspond to AN minus 1, right?
Yes.
Right. No, yeah, we should talk about this.
Yeah. Absolutely.
Yeah. Because also AN plus 1 is a 1-point extension by a projective. I think I could, yeah. So you have, so essentially if you have A3, so A3, suppose that you take this A3 here, you have this arrow here. So this is, so okay, this is the 1-point extension of this arrow by this point. And then this guy is the 1-point extension of this algebra by this point. And yeah, I don't know, we should definitely talk about
Yeah,
this.
okay. So what you're essentially saying is that you can build this quiver by first putting 1 and then adding 2 and the arrow and then 3 and the arrow, or you can go the other way back and just start at the end.
Yes.
And then add. Okay,
yeah,
so
or you
these are
quotient.
precisely the two procedures I was talking about.
Right. Yeah, you could quotient and get from this to this somehow. Yeah.
Okay, so we definitely have to.
Yeah.
This.
Yeah, definitely. The cool thing is that no, we definitely need to talk about it.
let's get on.
Okay.
Okay.
So, more questions? Okay. Bueno, muchas gracias, Hipolito. Okay.
I'm sorry, Hagen, you couldn't ask. Yeah, see you tomorrow. I think. Yeah. Okay.
Okay.
See you.
Gracias.
Bye bye.
Bye.
Ciao, ciao.
Bye. Ciao.